So yeah, it probably would have been good if I would have used this example earlier instead of that more complicated 128-bit times 128-bit thing, but I just come up with examples randomly as I thrash around, and then I just put them in whatever order I found them. So here we go. This is a situation where the compiler generates a mul-h instead of a mul-hu, and for that to occur, the compiler has to be thinking that it is multiplying two signed xlang-sized arguments times each other. Now, in this case, it appears that the compiler recognized that the A2L, the ASCII string to long, which is a signed long, it recognized that the maximum value for this would be a 32-bit value. And so although it's storing that into the A128 as the initializing value, it's really just a 32-bit value signed extended up to a 64-bit value signed extended up to a 128-bit value. So when it subsequently sees that it's being multiplied by itself, it's recognizing that, well, we're really just doing a 32-bit value times a 32-bit value, but just in case that would have been a 32-bit signed value that would have got extended up to a 64-bit signed value that subsequently would be a 64 times 64 value stored into 128s, it's going to basically just generate a mul-h and a mul. The mul-h giving you the high order bits and the mul giving you the low order bits, and it's optimized for smallest size, which is why, there's this intermixing of basically the initial setup of the stack, and then the teardown of the stack even starts before they do the final mul A0 times A0, where A0 was just the output of the A2L. So basically that A0 would have been the sign extended 64-bit version of whatever 32-bit value it took in from the A2L. So 64 times 64, store it back out into the lower bits, A0 being the lower 100 of the 128 bits, A1 being the higher of the 128 bits. So just per the ABI conventions, placing the return values in A0 and A1 for a 128-bit value. If this was not a 128-bit value, and if you just changed this to like a 64-bit value, like signed long, you would not actually still get a mul-h to get the upper bits because it would have been truncated down to 64 bits, and a mul would have done the job. So that's the takeaway from this. You need to have something that can at least store 2 to the xlang bits for you to see the calculation of the upper xlang bits. Okay, and that is our mul-h. So we've got mul, we have mul-h for the high bits. We saw previously mul-h for the high bits, treating the arguments as unsigned. And coming up next, signed times unsigned.